we'll continue with our next numerical now. I'll read the numerical here. See, they analyze the continuous beam using slope deflection method. Conditions are given to you. Support B is sinking by 2.5 mm and the I value, that is moment of inertia value, is given to you 3.5 into 10 raised to 7 mm raised to 4 and E is given to equal to 200 kilonewton per mm square. This is the loading diagram. The difference in this loading diagram is, up to now the previous numerical whatever we have seen, those are your 2 span continuous beams over here. This will be your 3 span continuous beam. So what difference it makes, that we'll see further. Also it is asked you that you have to plot the bending moment diagram by superposition and also you have to draw the shear force diagram in this. Shear force diagram we have not seen in your previous numerical, so we'll see that concept in your this numerical over there. Loading in span AB UDL is given to you, in span CD again UDL is provided to, and in span BC a point load is provided at the center over there. Okay. So initially what I'll do, I'll make some conversions over here because whatever I value and E value, those are given to you separately over there. In numerical I will require the EI value over there, so I'll see for that. So whatever EI value that you want, that shall be in kilonewton meter square. That shall be in kilonewton meter square. Now if you observe these values, this is given in mm raised to 4 and this is also given in mm square over there. So we need to convert that into meters over there. So we'll see first for I value over there. I value, that is given to 3.5 into 10 raised to 7 mm raised to 4. So if I want to convert mm to meter, that becomes 10 raised to minus 3. So this will be 3.5 into 10 raised to 7 as it is, multiplied by 10 raised to minus 3 raised to 4, and that is converted to meter raised to 4. So if I simplify this, I'll get 3.5 into 10 raised to 7 multiplied by, this becomes indices multiplication, that is 4 into 3 will become 12. So on further simplification, I'll get this as 3.5 into 10 raised to plus 7 minus 12, that I get as minus 5 meter raised to 4. So this will be my I value over it. Okay, then I'll convert now my E value. E is given to 200 kilonewton per mm square. Now whatever value I require, that is already in kilonewton. Here it is kilonewton, so no need to convert kilonewton to newton. Just what we'll do, we'll convert mm square to meter square over there. Okay, that is 200 into 1 upon 10 raised to minus 3 square, that becomes kilonewton per meter square now. Getting this? So is equal to 200 into multiplication of indices, 3 into 2, that will become minus 6. When it goes on upward side, that becomes 10 raised to 6. So that value comes 200 into 10 raised to 6 kilonewton per meter square, or you can say 2 into 10 raised to 8 kilonewton per meter square. Okay, now I'll take multiplication of these two values, that is I'll require EI value. So E I have got equal to 2 into 10 raised to 8 kilonewton per meter square multiplied by I value, that I have got 3.5 into 10 raised to minus 5 meter raised to 4. So here meter square and 1 meter square will get cancelled. Here meter square will remain. So this becomes 2 into 3.5, that becomes 7 into 10 raised to 8 into 10 raised to minus 5. Here addition of the indices will become, so 8 minus 5, that become 10 raised to 3 kilonewton. This as it is multiplied by this meter square remaining here. So EI value I can say that it becomes 7 into 10 raised to 3 or 7000 kilonewton meter square. Okay, so in some numericals this tricky process is given to you, that is if EI conversion is not given to you, you have to convert that in this way or this. So EI I am getting here equal to 7000 kilonewton meter square. Remember, unit of this shall be in kilonewton meter square. Now this EI value, where we have to substitute, we have to substitute while calculating the slope deflection equation in 3 delta upon L, that is rotation due to translational displacement over there. Okay, now we'll start with our general steps over there. Okay, so our first step is what? First step will be calculating dk value over here, that is degree of kinematic indeterminacy. So that is dependent on your support conditions over here. Okay, so if you observe support A and D both are fixed over here, that is decay value will remain here 0. Okay, while B and C, those are your simple support or hinge support over there, that is decay value at point B will be 1, that is theta B, and decay value at point C will be equal to 1, that is theta C. So total decay value will become equal to 2, and those are theta B and theta C. This will be called as your unknown displacements. Okay, that we are going to find out, and the known displacements are what? Theta A and theta D, those will remain 0. Those will be called as your known displacements. Okay, then we'll proceed to our second step, that is calculating the fixed moments, FEM. Okay, so first fixed moment, that is MFAB. MFAB, initially what we do, we consider all joints as the fixed joints over there, and fixing joint B and C also. Fixed moment in span AB loaded completely with UDL, that comes equal to minus WL square divided by 12. So if you calculate this value, that comes equal to minus 30. All these values are in kilonewton meter over there. Okay, next fixed moment I'll see MFBA. So that will remain plus WL square by 12, since your restoring moment will be clockwise in nature. If you calculate that, that will come plus 30. Next I'll see MFBC. In span BC, I can consider in both ends as your fixed one, point load loaded at the center over there. So your fixed moment will come minus WL divided by 8. So if you calculate this value, W is your 100, length of span BC is 2 meter. So W 100 into 2 divided by 8, that gives you equal to 25. Same way, if I calculate MFCB, I'll get plus WL by 8, that is I'll get equal to plus 25. Same way, in last span now, MFCD I'll get. Again in span CD, it is loaded completely with the UDL over there. So that comes again minus WL square upon 12. Restoring moment is anti-clockwise, so that comes negative here. So W here is your 50, length of your span is 3, so 50 into 3 square divided by 12, that comes equal to minus 37.5. and same way MFDC, that will come plus WL square by 12, that is equal to plus 37.5. so this will be my final fixed moments over there. Then we'll proceed to your next step, that is step number 3. We'll plot your slope deflection equations. We'll plot your slope deflection equations over there. We'll see for your first member, that is MAB over there. Okay, now in this numerical, one condition is given to you, that your support B is sinking by 2.5 mm, that this support B, it is sinking downward, that is 2.5 mm over there. So what are translational rotations will be induced, that this support B will be inducing that in member AB and in member BC. That will not be induced in member CD over there. Only in just member AB, BA, BC and CB, your this translational rotation effect will be seen over there. That will not be seen in member CD and DC. That is for CD and DC, your this delta value will remain 0. That is, or you have to calculate that value for AB, BA, BC and CB equations over there. So we'll see one by one. That is first equation MAB. I'll write directly the values. So equation for MAB, it is equal to MFAB, that we have calculated as minus 30 plus 2EI upon L. I value is given to you throughout the same over there. That is no variation of I value is there. So that is minus 30 plus 2EI upon L. L is your 3. So that becomes 2EI divided by 3 into bracket. Near end is your A, far end is your B, but near end is your fixed one over here. That is your theta A value comes here equal to 0. So I'll get directly theta B minus 3 times of delta divided by length of your span is 3 meter. Now considering this sign of delta over there, that we have to see over there. Suppose this is your member AB and this is your member BC over there. Okay, this support B, it is sinking downward by 2.5 mm over there, that is inducing a translational rotation in this member AB also and this in member BC also of intensity how much, that comes equal to, this will observe a anti-clockwise rotation and here you will see the clockwise rotations over there, that is here I will get 6 EI delta upon L square, anti-clockwise we take here positive, same way plus 6 EI delta upon L square, and for BC member you will get minus 6 EI delta upon L square and again here minus 6 EI delta upon L square. That is for member AB and BA you have to substitute delta value as positive, that is delta will be equal to plus 2.5 mm. Okay, and same way for span BC and CB you have to substitute that delta as minus 2.5 mm over there. Okay, so here I'll substitute your delta value over there, so I'll get equation of MAB as minus 30 plus 2 by 3, that comes equal to 0.67 EI into bracket theta B minus 3 will get cancelled, just delta will remain, that is 2.5, this is given in mm, I'll consider that in meters, so I'll get 2.5 into 10 raised to minus 3. Now what I'll do, I'll multiply this term to this inside bracket over there, so I'll get this as minus 30 plus 0.67 EI into theta B and minus this I'll get as 0.67 EI into 2.5 into 10 raised to minus 3. EI value, that is you have calculated, it is equal to 7000, so we'll multiply that 0.67 into 7000 into 2.5 into 10 raised to minus 3 over there, that I get 0.67 into 7000 into 2.5 into 10 raised to minus 3. So I get this value as minus 11.725. Okay, so if I simplify this equation further, that is MAB I'll get as minus 30 minus 11.75, that is I'll add 30 in this, I'll get as minus 41.72 plus 0.67 EI into theta B. So I'll call this as my equation number 1 over here. Okay, now in same way we'll see for your next equation, that is equation for MBA. Okay, MBA, it is equal to MFBA, that we have calculated as plus 30, so plus 30 plus 2 EI upon L, that I'll get as 0.67 EI into bracket, now your near end is your B, far end will be your A, so I get this as 2 times of theta B minus 3 delta upon L is again your 3. Okay, so this delta, that will remain again positive over here, that is for BA also we have to treat that as positive, 2.5 mm. So this, whatever this value we have calculated, that is 2.5 into 10 raised to minus 3 multiplied by 0.67 EI, that will remain same as it is. So I'll directly simplify this, that is equal to 30 plus 0.67 into 2, that I get as 1.34 EI into theta B minus 11.725. So if I simplify this MBA, I'll get as 30 minus 11.725, I get that as 18.275 plus 1.34 EI into theta B. So this will be my equation number 2 over here. Okay, we'll proceed to your next member now, that is MBC. MBC, it is equal to MFBC. So MFBC I'll get as minus 25, got that, plus 2EI upon L. L of member BC is your 2. So 2 by 2, that will become 1. So simply EI I'll write here into bracket. Near end is your now B. Far end will be your C. So I'll get this as 2 theta B plus theta C minus 3 delta upon L. Now if you observe this, for BC and CB member, you have to substitute that delta as negative. So that minus will make this sign as plus over there into 3 delta divided by L for member BC, that is equal to 2 over here. Okay, so we'll substitute the values over here, that is minus 25 plus, I'll separate this EI to these terms over there. So EI into 2 theta B plus theta C plus EI into 3 into 2.5 into 10 raised to minus 3 divided by 2 over here. Okay, so I'll simplify this. I'll substitute EI value over here. So EI that I have got as 7000 multiplied by 3 into 2.5 into 10 raised to minus 3 divided by 2. So this term I am getting as plus 26.25 over there, and minus this 25 I get total term as 1.25 plus EI into 2 theta B plus theta C. So this will be my third equation over there for MBC. Okay, now we'll see next equation, that is for MCB. MCB, it is equal to MFCB. MFCB we have calculated as plus 25. So plus 25 plus 2 EI upon L, that will come again EI. Okay, into bracket. Now here your near end is C, far end will be your B. So here what will get changed? This will become theta B plus 2 times of theta C plus 3 delta upon L, that is equal to 2 over there. That is length of CB is 2, and due to delta sign convention this will become again positive over there. So we'll substitute the values, that is plus 25. EI I'll separate to both these terms. EI into theta B plus 2 times of theta C plus EI into 3 into delta is 2.5 into 10 raised to minus 3 divided by again 2. So I'll simplify this for MCB equation. Okay, so EI I've got as 7000 into 3 into 2.5 into 10 raised to minus 3 divided by 2, and this plus 25 will get added to that. That is equation I'll get as plus 51.25 plus EI into theta B plus 2 times of theta C. That will be my equation number 4 here. Okay, now next span will move, that is your 3 span beam. So your one more span is added. So next equation will be your MCD. Okay, for MCD we have calculated MFCD equal to minus 37.5 plus 2 EI upon length of your member CD is 3 into bracket. Near end will be your C, far end will be your D, but far end rotation D theta D is 0. So what will remain? Just 2 times of theta C, and here your delta will not be considered because sinking of support B will be only for member AB and CB. It will, delta value shall not be considered in member CD and DC over there. So here your delta value will remain 0. So if I simplify this, MCD I'll get as minus 37.5 plus 2 by 3, that will become 0.67 multiplied by 2, that becomes 1.34 EI into theta C. That is my equation number 5. And the last equation we'll see, that will be for MDC. It is equal to MFDC plus 37.5 plus 2 by 3, that I'll get as 0.67 EI into near end is your D, but that is 0. Far end rotation will be your just theta C. So this will be my equation number 6 over here. So for 3 span beam you will get total equations equal to 6. Okay, so this will be my 6 numbers of equations over there. Now we'll move to your next step, that is step number 4, conditions of equilibrium. Now conditions of equilibrium shall be equal to your value of decay numbers. that is in case of beams and non-sway frames over there. Okay, so dk value you are getting here equal to 2. So two conditions of equilibrium will be there. So first condition we'll see. Now see, you have to just observe the incapable supports over where your bending moment shall be 0. So at A and D, those are your fixed supports, so those will be your capable supports. So no zero bending moment will be seen at A and D. Okay, likewise at B, this will be treated as your rigid joint. So summation of moment of MBA and BC shall be equal to 0. That will be my condition number 1. And next condition will be at C, that is summation of moment MCB and MCD shall be 0. So to keep those joint B and C in equilibrium over there. So first condition is what? At support B. At support B, that condition is what? That is MBA plus MBC shall come equal to 0. Okay, I'll substitute the equation of BA, that is equation number 2 here I've got. Okay, that is equal to 18.275 plus 1.34 EI into theta B over here plus next equation I'll substitute of BC, that is your equation number 3 here. Okay, that is 1.25 plus EI into 2 theta B plus theta C is equal to 0. Okay, I'll simplify these equations over here. Therefore, see what I get. I'll add first constant terms over there, that is 18.275 and 1.25. 18.275 plus 1.25, I get that as 19.525. When it goes on RHS side, that becomes equal to minus 19.525. Okay, then we'll see here theta B and theta C terms now. Now from this both terms, I'll take EI common over there, and that EI will get divided to this 19.525. Okay, so what will remain? Just we'll see theta B terms, 1.34 times of theta B and 2 times of theta B. So 2 plus this 1.34, that gives me 3.34 times of theta B. And next here there is no theta C term, so here only one theta C is remaining, that is plus theta C is equal to minus 19.525 divided by EI. That will be my first equilibrium equation number A. Okay, now second equation that we have seen for at support C. Okay, at support C, members meeting at support C are, that is condition will be what? MCB plus MCD shall come equal to 0. Okay, I'll substitute the equation of CB, that is equation number 4th I have got 51.25 plus EI into theta B plus 2 times of theta C plus next equation of CD, that is equation number 5 I have got minus 37.5 plus 1.34 times of EI into theta C is equal to 0. Simplification is very important in your this numericals over there. So we'll simplify this. 51.25 minus 37.5, 51.25 minus 37.5, I get this as 13.75. so when it goes on RHS set, that will become minus 13.75, and EI I am taking common, that will get divided over it. Okay, so here what will remain? Just this term we have to simplify this. Okay, so here theta B, here there is no theta B, so 1 theta B will remain, plus here 2 times of theta C, and here 1.34 times of theta C, that is 1.34 plus 2, I'll get 3.34 times of theta C is equal to minus 13.75 upon EI. That will be my equilibrium equation number B over here. Now I'll solve these two equations, that is solving equation A and B simultaneously for the values of your unknown displacement, that is theta B and theta C over there. Okay, we'll solve these two equations over there. Mode 1, number of unknowns here are 2, that is first term I am getting 3.34. okay, second term I am getting equal to 1, next minus 19.525, next second equation now 1, here I am getting 3.34, and last time I am getting constant minus 13.75. So this x value, that will be your theta b value, minus 5.06 divided by EI, and next value that will equal to b minus 2.599. So I'll write that as directly 2.60 divided by EI. So these two values I am getting here as your basic unknown values. Okay, so here these values you have to substitute in your this basic 6 slope deflection equations to get the values of final moment. So we'll move here to proceed last step, that is final support moments over there. Okay, so substituting this theta b and theta c, I have calculated the value of MAB, that will get as minus 45.11 kilonewton meter. You check these values. MBA you have got plus 11.49 kilonewton meter. Next MBC value I have got minus 11.49 kilonewton meter. Next value of MCB 41 kilonewton meter. MCD I have got minus 41 kilonewton meter, and the last value MDC I have got plus 35.75 kilonewton meter order. So these 6 values I am getting. You check the values, and if you find any query in these values, you please comment over there. Okay, so this final moment or final support moments I am getting here. Now using the support moments, what you have to do, you have to plot the bending moment diagram over there. Okay, so for bending moment diagram we know the sign convention over there. I'll not repeat those sign conventions again. So first I'll mark all the points, that is your support A, support B, support C, and support D over here. Okay, so we'll see one by one. That is MAB I am getting minus 45, minus it is, so it will be plotted on upward side over there. Okay, so this I am getting as 45.11. Next BA moment I am getting as plus 11.49. So somewhere here it will be 11.49. Now next span, that is your for span BC over there. For span BC is your A, B, C and D. Okay, for span BC, MBC are getting minus 11.49, already it is plotted. Next MCB, that I have got as 41 over there, positive it is, so again it will go on upward side over there. Next span CD, so MCD I am getting minus 41, already it is done here. MDC, that I am getting as 35.75, and just simply what you have to do, you have to join these points using a straight line over there. Okay, so this will be our plotting of support moments. Now we have to plot your span moments over there. So span moment will calculate here maximum span moments. Okay, those are for span AB, for span BC, and for span CD over there. Okay, so if you observe the loading, in span AB there is UDL, and in span CD there is UDL over there. So maximum moment here will be WL square divided by 8 and WL square divided by 8 for AB and CD over there. And in span BC there is a point load loaded at the center, so that becomes equal to direct WL divided by 4 over there. So if you calculate this value, I have got this as 45 kilonewton meter, this I have got as 50 kilonewton meter, and this is a 56.25 kilonewton meter. So in portion AB, that will follow parabolic path since it is a UDL. Okay, somewhere here maximum at the center, that is WL square by 8, I am getting that as 45. Next in span BC, point load is there, so your nature of BMD will be a straight lines over there. Maximum at the center 50, WL by 4, that I am getting equal to 50. And last in span CD, again there is UDL, so it will follow parabolic path of 56.20. WL square by 8, it equal to 56.25 over there. Okay, and what you have to do, you have to just superimpose, you have to just shade the superimposed part over here. Okay, so that gives me total BMD by superposition over there. Just I'll write here superposition, so you'll understand it. BMD by superposition over there. Okay, here your numerical is not completed actually, because in the numerical what is asked you have to plot the bending moment diagram by superposition, and also you have to plot the shear force diagram over there. So we'll see how we have to plot the shear force diagram further. Okay, I will see for shear force diagram over here. Okay, see for shear force diagram what I am doing, I am separating my three members over here. That is, this is your member AB, this is your member BC, and here this is your member CD over here. Okay, I am keeping the loading same in it. Okay, for calculating the shear force diagram, what you have to do, you have to calculate the support reactions over there. That is, reaction at point A, reaction at point B, and reaction at point C and D also. This is your loading 50 kilonewton per meter over there. Length of your span AB is 3 meter. This is your 1 meter, again 1 meter, and this is again your 3 meters over there. Okay, here what I am doing, I am marking my reaction points over there. That is, suppose this reaction, it is here equal to RA or VA also you can say. This is your reaction RB1. This will be our second reaction, that is RB2. Here this reaction will be your RC1, this reaction will be your RC2, and here you will be having the last reaction, that is equal to RD over there. So initially what you have to do, you have to just separate your members over there, or separate your joints, and you have to keep the loading as it is given to you. Okay, now in this diagram what you have to do, you have to add your final moments over there. Okay, so final moments I have calculated over here. Okay, we'll see one by one over here. See, final moment, that is MAB, I am getting equal to minus 45.11. This is your support moment. So this will be your at support A, this will be your at support B over there. Likewise. Okay, so support moment at A, you are getting minus 45.11. What this minus is indicating, that your nature of moment will be anti-clockwise in nature, because we are assuming clockwise as positive over there. That is, this moment I will mark here anti-clockwise nature equal to 45.11. Okay, same way at point B I am getting it equal to 11.49, that is for your span BA. Or okay, so this is positive, so that will be clockwise in nature, that is 11.49. Same way for span BC I am getting negative 11.49, minus it is, so it will be anti-clockwise in nature. Next moment CB I am getting clockwise in nature, positive, that is 41. Okay, same way in span CD again negative 41 I am getting, that is anti-clockwise in nature, and here in span DC again positive moment I am getting, that is clockwise in nature, 35.75. So I have just marked my final moments over there. Now using this and using your equilibrium conditions over there, what you have to do, you have to calculate the values of these reactions over there. So first I am considering span AB over there. Okay, in span AB what you have to do, you have to take summation of moment either at point A or either at point B. I'll take suppose summation of moment at point A equal to 0, treating clockwise moments as positive over here. So whatever moments are acting, that will be taken over here. So minus 45.11, since it is anti-clockwise, that is negative, plus moment of this UDL along this point A, that will come equal to 40 into 3 into 1.5. You have to use SOM concepts over here, that is concept of SFD and BMD simple. Okay, next this moment plus 11.49, and lastly moment of RB1 along the point A, that will come anti-clockwise equal to 0. So if you calculate RB1 from this, you will get that RB1 is equal to 48.8 kilonewton, and positive you will get that is your assumed direction will be correct, it will be acting in upward direction over there. Okay, now second condition I will use, that is summation of Fy considering upward forces positive is equal to 0. So what condition I will get here, Ra minus udal intensity that is 40 into 3 plus this RB1 that is 48.8 shall come equal to 0. If I calculate this, I get my Ra value is equal to 71.20 kilonewton. Again positive I will get that is my assumed direction will be correct, so Ra is also acting upward over here. Okay, so that will be for your part or member AB over there. Okay, now same way you have to calculate the values of RB2, RC1, RC2 and RD over here. So if you calculate those values, you will get RB2 as 35.75 kilonewton upward over there. Okay, and here RC1 you will get as 64.75 kilonewton again upward. Same way in this next span, that is in span CD, you will get RC2 value as 73.75 kilonewton upward, and RD you will get directly equal to 76.25 kilonewton upward. So here RB1 and RB2 we have calculated over there. Okay, and RC1 and RC2 we have calculated, all are acting in upward direction. So we will write final reactions over here, that is here I will write RA, RB, RC and RD over there. So RA I have got 71.20 upward. Okay, RB that will be equal to summation of RB1 plus RB2, so I get that equal to 84.55 total acting in upward direction over there. Okay, same way RC I am getting as equal to 138.5 again acting upward, and RD lastly I have got equal to 76.25 again acting upward over there. Now using this I will plot the shear force diagram over there. Okay, this will be your point A, B, C, and this will be your last point D over there. Okay, now for shear force diagram we consider the sign conventions over there. This is your section XX. If forces are going upward to the left and forces are going downward to the right, that shear force we treat as positive shear force. And second sign convention, again section XX, if forces towards left are going downward and towards right those are going upward, that shear forces are treated as negative over there. So using this sign convention we will see over there. Now shear force at point A over there. Okay, considering the right hand side part, your reaction I am getting 71.20, that is upward. So directly your shear force at point A will be plotted on upward side, that is 71.20. Okay, now considering section on the left hand side of this RB over there. Okay, so what shear force you will get over here, that is UDL will be considered over here. Okay, UDL intensity, that is 71.20 minus to the left hand side of this section forces are going downward, those are treated as negative, so UDL intensity will be treated as negative, minus UDL is how much, 40 into 3. So here I get shear force on the left hand side of B is equal to 48.8 over there. Okay, then in portion AB you are having a UDL, so your shear force diagram will have a inclined line over there. Okay, now shear force to the right hand side of B over there, section passing to the right hand side of B, already we have calculated 48.8 negative. Okay, so plus what will get added, your reaction RB will get added into that, that is 84.55. so shear force on the right hand side of B I am getting equal to 35.75. Okay, now your shear force will get changed at this point load condition. Okay, up to here left hand side of this point load, this 35.75 shear force will remain constant. Okay, and to the right hand side of this point load over there, your shear force value will get changed, that is this plus 35.75, and this will be towards the right downward force, that will be treated as negative. So 35.75 minus 100, I'll get that as negative shear force equal to 64.25 over there, which will remain constant again up to this point C over there. Okay, to the left of point C. Now we'll see shear force to the right hand side of this point C. So what will get added? This minus 64.25 plus your RC reaction will get added, that is 138.5. I get that value as equal to 74.25. That will be your shear force to the right hand side of point C. Okay, now again in portion CD you are having UDL over there. So shear force at point D, will calculate that. So whatever this 74.25 positive I've got minus your UDL intensity, that will be equal to 50 into 3. You shall get this value equal to your RT reaction value. See, this I am getting as 75.75 and your RT is almost same over there. Okay, so whatever this shear force that I get as equal to your, I'll write directly RT value, that is 76.25 over there, and this again in portion CD, this UDL you are having, so it will be joined by a inclined line over there. So this will be your positive shear forces portions, and this will be your negative shear forces portion considered from line 0, 0 over there. So this will be your complete shear force diagram over here. Okay, hope so you have understood this concept of shear force diagram. If you are having any problem or any query in drawing shear force diagram, you can comment in the comment box over there and you can ask your queries. Okay, so this will be your final lecture for your non-swept frames and your beams over there. From next video we'll start with your sway frames over there. Okay, thank you so much.